Hi there, it's Marco from Donut Lab. You are watching our battery proof series called I Donut Believe. In this series, we demonstrate the capabilities of Donut Battery, which is the world's first solid-state battery used in production vehicles. Today's topic is fast charging test. This test shows how the Donut battery cell can take a typical 1-hour charge event as well as extremely rapid charge events with around 0 to 80% in 10 minutes and in 5 minutes. The test is first performed with 2 passive aluminium heat sinks on both sides of the battery cell. This is done to simulate the cell being a part of a typical battery pack with not so great cooling. The second part of the test is done with 1 heatsink removed, simulating a very bad cooling design. The sweet spot of the Donut battery cell is in the more hot environment, so even very bad cooling design is actually pretty good for our cell. These 2 phases are done to compare how different temperatures affect cell performance, giving a hint towards how this cell would operate in different battery module and pack designs. Now let's go and watch the test.
Thanks, Marco. We're here at the VTT Battery Lab looking at independent third-party test results of our solid-state battery cell. The VTT is the Technical Research Center of Finland, a Finnish government-owned research center. The full report made by VTT is available to download at idonutbelieve.com. So let's dive in. Before we go into test setups, let's take a moment to explain what we are testing and why that matters. This test is about charging speed and thermal stability. In simple terms, we are measuring how fast this solid-state battery can be charged and how well it behaves thermally while doing so. This test setup does not try to simulate operation in an actual battery pack, but instead this is showing a sort of worst-case scenario where there is no active temperature control and the cell is free to rise in temperature with these incredible high C rates. Although this test is not simulating how the cell operates in a full battery pack, it does also give us a nice look into how easy this cell is to package into a battery pack. Because one massive problem for typical solid-state batteries so far has been that they require a strong clamping force for each individual cell, or otherwise the active layers inside the cell can separate and then the battery kind of doesn't want to be a battery anymore. And not only that, but typical solid-state batteries also swell and shrink during cycles, and this breathing can be as high as 15 or even 20% of the cell volume. That means maintaining that difficult clamping pressure becomes even more difficult, leading to a seriously overly complicated battery pack design. Now this, according to many of our customers, means that any performance gain they get on a cell level basically is lost at the pack level again, leading to a more expensive pack that has roughly the same energy density and performance as a conventional lithium-ion pack. These challenges have been deal breakers for many of our customers to use solid-state batteries so far. But in the Donut Lab batteries, we do not have these limitations. About the numbers we are saying, so charging speed is expressed using something called a C rate. So 1 C charge means the battery is charged from 0 to full in 1 hour, and 2 C means half an hour, and 3 C means 20 minutes, and so on. So most conventional lithium-ion batteries are designed to charge at around 1 or 2 C, sometimes even 3 C for a short amount of time under very active cooling. But going beyond that usually leads to problems like damaging the cell and therefore reducing the lifetime dramatically. Or in worst case, of course, thermal runaway, because it's difficult to maintain the cell in its normal operating window. We are going way beyond this in this test. So 5 C charge corresponds to 100% charge in roughly 12 minutes, and 11 C charge corresponds to 100% charge in about 5 to 6 minutes. And with that context, let's take a look at how this test was set up and how it was conducted. The purpose of this test is to provide 2 different data points for how the cell performs in different cell temperatures. The first test setup was 2 passive aluminum heatsinks gently pressed together with simple clamps. Now this is not to provide the clamping force for the cell like we mentioned earlier, but this is instead just to gently provide a good heat bath to reduce hotspots, especially around the tabs. And the second setup was 1 heatsink just at the bottom so the cell is just lightly taped on one side. The test started by conducting our standard 1C discharge capacity test to set a good nominal capacity benchmark to compare against. Then the cell went into fast charging tests. Both 5C and 11C tests were first run with 2 heat sinks and then again with just 1 heat sink. But for sake of clarity, let's compare results with 1C rate at a time. In the 5C tests, the cell was charged with 130 amps using 4.3 volt charge voltage. With 2 heat sinks, the cell can take that stable 5C for more than 9 minutes, making it reach around 80% charge in less than 10 minutes. Cell temperature only rises to around 47 degrees Celsius. Then, with only 1 heatsink, cell temperature rises more during the test, so to around 62 degrees Celsius at its very peak, which lowers the cell internal resistance enough to make the cell perform even better. You can see the rise in cell voltage during charging is lower with just 1 heatsink, making the cell be able to accept a constant 5C for a full minute longer before limiting the currents. This makes the 0 to 100% charge take only just over 12 minutes, more than a minute faster than with 2 heatsinks. With 11C, the difference between these two setups is very similar. With 2 heatsinks, the cell can accept that full 11C charge for around 3 minutes, and it reaches 80% state of charge in less than 5 minutes, with the cell temperature at its very peak only rising to 63 degrees. With only 1 heatsink, cell temperature rises to 89 degrees at the peak, which is still very much in the comfort zone of this cell. You can see in the graphs that this higher temperature rise makes the cell voltage actually drop in the early phases, even though we use a 4.3 charge voltage throughout these fast charging tests. This allows the cell to accept that full 11C charge for around half a minute longer, which means it reaches 80% state of charge at just over 4.5 minutes. And it also reaches 90% and 100% state of charge around half a minute sooner than it did with 2 heatsinks. So from these tests, we can conclude that these cells have a very wide comfort zone for different cell temperatures and charging speeds. But please note that these curves and values can have a lot of variance based on the very specifics of the cell test setup. But these tests clearly show that these cells can take these kind of incredible charging speeds even with no active temperature control. This gives you a hint for how this cell could perform as a part of a battery pack with active cooling and active temperature control. And these tests also show how simple a battery pack architecture can be using these cells. Because with no special requirement for that clamping force for individual cells, and with a very high performance even with passive cooling, these cells can reach very high performance in a simple and low-cost battery pack design.
That's everything this time. Thank you for watching. The full report is available for downloading at idonotbelieve.com. Thank you so much, and see you next time.